Hello everyone. So now we will introduce the idea of cyclic prefix or CP. So any frequency selective channel can be modeled as using channel taps or like S0, H1 or HL-1, say to Lth. So this is any frequency selective channel and these are the taps. So what happens because of this channel? If you see any signal at timestamp n, yn, then it will be S0, xn, and h1, xn minus 1 plus so on and so forth. The last one is hl minus 1, xn minus l minus 1. So you also have the contribution of previous L minus 1 symbols, which is the interference term. Or if you have two OFDM symbols, say this is your current OFDM symbol, which is, say, these are the samples, x0, so on and so forth, xn minus 1, and say this is the past, which will be x n minus 1, and this is x0. So if I calculate y0, this will be given by S0, x0 plus h1 n minus 1, so on and so forth, hl minus 1, x n minus l minus 1. So basically this is your desired signal, but it also has interference. This is interference. This is the desired signal. So how to get rid of this interference? So what happens? Your initial signals will be actually affected by the previous signals. So this is NB, and these are parts of initial signals, the dash ones, they are affected by your previous signal. So how to get rid of this, this interference? So in order to do away with this interference, we come with an idea of cyclic prefix. So what actually is done in cyclic prefix? Suppose these are your samples, x0, x1, x2, x3. Now, in some part of the signal is actually repeated in the beginning. So this is actually cyclic prefix. I have shown here only one, but actually it depends on the delay spread and other factors, how many will have to be prefixed with the symbol, OFDM symbol. So right now I have done only x3, which is prefix. So this is called a cyclic prefix, and let us now try to understand how this will prevent this intersymbol interference. So if I take these samples, say this was x0 sample, or this was x1 sample, this was x2 sample, this is x by 3 sample. They have different values. and suppose S0 and H1, they are the taps. The channel is modeled using S0 and H1. Then let us see for k is equal to 0, for example, or k is equal to 1, or k is equal to 2, k3. So this k is equal to 0 will be, this will be S0 here, and it will be affected by x3. So H1 will be multiplied by x3, and for k1 it will be H1 and H0, and others are 0. For k is equal to 2, it will be 0, H1. I mean, you can write these equations, or I have written here. H1, this is k is equal to 2, S0, 0, and this is H1, this is S0, this is 0. So yk in this case, when it is, there is a prefix here, will be given like this, and for y0, 1, 2, 3, and this is the noise part, noise sample, will be given by S0, X0, H1, X3, and so on and so forth. So this is what I have drawn here. And if you see here, there is a circular shift of channel taps. There is a circular shift of channel taps. So it is actually H1, 0, H1, 0. So this is a circular shift of, you can see that trend happening, H1, 0, H1, 0, then H1, 0. There is a circular shift. So effect of cyclic prefix is to convert this into a circular convolution. Earlier it was a linear convolution. So CP, cyclic prefix, actually has converted linear convolution into circular convolution. So this is what the cyclic prefix has done, and this is clear from this simple example where I have used x3 as the cyclic prefix to the samples x0, x1, x2, x3. So y is actually, this is circular convolution. This is circular convolution. This is different from linear convolution. And this is the noise part. So y has become h, circular convolution, plus x plus v. Let us take FFT, because we are doing the FFT operation on the receiver. FFT of y will be FFT of whole thing. And this can be broken, FFT of h, circular convolution x, plus FFT of noise. So this is a property of circular convolution. This can be broken into FFT of h into FFT of x plus FFT of y. So this gives you y is equal to hx, and this is some quantity noise. So this will be direct multiplication in case of circular convolution. So this is actually, so this becomes y is equal to hx, or yk for each subcarrier is actually hk xk, plus of course some noise which we are just adding here. So this is nothing but n point DFT of yk. This is n point, this hk, n point DFT of h after you have added padding, after adding 0 padding, because it is S0 and H1. So so I'm counting others as 0. So you have added them as 0, and then after adding this endpoint DFT, after adding after adding padding with 0. So this basically gives you the output. So basically the output is nothing but the channel coefficient and the symbol. So what essentially channel coefficient, that is Hk into symbol. This is capital Yk. So what actually has happened here, earlier we started with something which is frequency selective single carrier, frequency selective single carrier. Now we have broken this into n parts, each modulated by subcarrier. So we have made n parallel streams, and all those parallel streams were combined and they were transmitted. So the whole thing is converted into small parallel streams. This is what we did in MCM, multi carrier modulation, and this was frequency selective, and from this it is very clear that each subchannel is flat channel. So there is no question of ISI, no ISI. Then ISI was the main culprit in single carrier frequency selective channel, and we have converted this into n parallel subchannels, and each subchannel is now flat channel. So the ISI problem has been resolved. So by simply doing cyclic prefix, we are able to convert the channel into a flat channel, n flat channel, and there is no effect of, or there is no ISI now happening among the symbols. So now we are in a position to draw the complete diagram of OFDM transmitter and receiver. So this is your input stream. First operation, what we do is serial to parallel. So you get this different data, x0 to x minus 1. And then we do IFFT. This is quite common IDFT algorithm, IFFT endpoint. And then you get these symbols here. This is xn minus 1. And then these samples are parallel to serial. And once you have done the serial, then you add CP. This is the add CP, cyclic prefix. Now we have understood why we want to add CP. So these are the samples which are transmitted. Samples at rate B. Now these samples, the first thing is CP is removed on the receiver, CP remove. Then serial to parallel. This is serial to parallel. You get these samples out. And then you do the endpoint FFT operation to get the data symbols out, because the coefficients of FFT operation is nothing but data symbols, x n minus 1. And then you do parallel to serial to get the output stream. So this becomes a complete OFDM diagram. So now let us understand OFDM transmitter and RX with CP, how normally it is done. So this is your current block, x0 to xn minus 1. These are the samples. And depending upon the delay spread, TD, you select those samples and prefix it in the middle, in the beginning. So this is what is the CP, and I have selected the LC number which are prefixed. So this becomes OFDM symbol, complete OFDM symbol. And because of this addition of CP, there's a loss in efficiency. So this is CP length, and this is a total OFDM symbol length. This gives you the loss in efficiency. So the CP is actually L minus 1 here. Yeah, L minus 1. So this C can be removed. And the total length will be N is because of this samples, and L minus 1 is your CP length. So the total loss in efficiency becomes L minus 1 N plus L minus 1. So as N tending to infinity, this loss is actually 0. But we cannot make N infinity, because if you make N infinity, that means there are many symbols which have to be collected at the receiver before they can be decoded. So basically the time for decoding increases. So the overall system becomes slow. So that is why N cannot be made very high. So there has to be a compromise on the decoding delay. There's a trade-off between N and decoding delay. So let us see how this number of symbols which have to be prefixed are selected. So basically this L is a number of symbols which are to be prefixed into TS. The duration of each symbol should be greater than or equal to TD. TD is the delay spread. So one has to meet this condition. This is delay spread. So we know TS is equal to 1 by B, and TD, we know this is approximately 1 by BC. BC is the coherence bandwidth. So from wireless course, we should know that the delay spread is equal to 1 by BC. This is coherence bandwidth. This is approximately given by 1 by BC. So LC becomes, from the earlier equations, TD greater than TD by TS, and TD by TS is nothing but B by BC. So this gives me N should be greater than L, should be greater than B by BC. Or the BC should be greater than B by N. Now let us understand this. So these two equations have come from whatever I had written in the last slide. So this BC is the coherence bandwidth, and this is your subchannel. B by N is subchannel bandwidth. So if BC is greater than the subchannel bandwidth, then there is no, the system is actually flat channel. This we have seen. We have come back to the same condition. All right. So let us understand an example. If N is equal to 256, that is the number of subcarriers, and BS is say 15.0 625 kilohertz per subcarrier. So B by N, this is B. This is actually B. This is B. This is not correct. So B is 15.625 kilohertz. So B by N, or I'm sorry, so this is, your B is 4 megahertz. So B by N will be 4 megahertz divided by N will give you 15.6 kilohertz. So this is per subcarrier. This is what I have written here. So this becomes your B by N. So if you see this BS, and your BS for a wireless channel is 250 kilohertz, this BS is much less than BC. So OFDM symbol time without cyclic prefix will be N by B. This is symbol time. N is equal to 256 and B, or bandwidth, is 64 microsecond. So in 4G, for example, 12.5% of the symbol time, that is of the 64 microsecond, is kept for CP. So CP, 12.5% of 64 microsecond will be 8 microsecond. So the total OFDM symbol duration, which will be CP, and the 64 which has come earlier, let us see this, 64 is N by B, OFDM symbol time without CP. So this is without CP, with CP is 8. So this is the total OFDM symbol duration, which is 72 microsecond. And number of samples, if you see in CPs, the CP duration is 8 microsecond. This is, we have seen earlier slides, and sample time is 1 by B. So the samples in CP which have to be prefixed are actually 32. So LC is equal to 32 samples, and total number of samples will be 256 was without CP, and 232 is, the CP samples. The total becomes 288. So if you want to draw, so this is your CP. CP, this is 8 microsecond. This one 8 microsecond which we have taken, and this was 64 microsecond in this example, and this is 256 OFDM samples, and this is 32 samples. So this is what is, so this whole thing becomes, total number of samples will be 256 plus 32, so this total will be 288. So and loss in spectral efficiency will be 32. 32 is the CP sample, cyclic prefix, and the total is 288, which gives you 11.1 percentage. 11.1%. Now let us try to calculate the BR for OFDM, bit error rate for OFDM. We had calculated for baseband, so we will also calculate for OFDM. So right now it is nothing to do with optical wireless channel. Right now I am discussing about the fundamentals of OFDM and how it behaves in RF channel. So as we have seen in OFDM, Y is equal to Hx plus noise, and for each subcarrier Yk will be Hk xk plus nk. This is what I have written. And nk we know is FFT of the noise samples at the output of the Rx, where these NM, this NM, they are the additive noise samples for each output sample. And this is NK is the FFT of the noise sample. Remember, we have done FFT operation in the receiver in OFDM. So if you take the expected value of NK of this FFT of the noise sample as the output of the receiver, expected value of this, you can take the expected operation here. This is e raised to power minus j 2 pi km, expected value of Nm. And also if I calculate the variance of this Nk, the FFT of the noise samples, variance of Nk whole square will be given by expected value of Nk is from here, this into conjugate of this. So this is the conjugate part. So you simplify this. This will give you expected value of double summation Nm into n conjugate L e raised to minus j 2 pi m minus L k by n. Now this expected operator can go inside, summation can come inside, and this can also is outside the expected operator. So this gives you because each component Nm into n conjugate L will give you sigma n square. This is only valid for L is equal to m, and then this is summed over all the subcarriers, which will give you n times sigma n square. So this is the variance. So the variance has increased, it has become n sigma n square. And let us do the same operation for Hk. Hk is given by these are the L paths. Remember we had L tap filter. So H will have value from S0 to HL minus 1 into e raised to minus j by 2 pi km into n. This is actually from this equation. So I am trying to calculate the FFT, endpoint FFT of H. So take the square, and so this is assuming this is these taps, these taps. Let us assume that these taps they are complex Gaussian distribution of mean 0 and variance n 1. So this will give 1 variance actually, and this summed over L times. So 1 plus 1 plus L times, what we get is L. So this total signal to noise ratio, this is the HK component L, and this is the power. This is the power, and the noise was actually n sigma n square. This was the noise. So total noise is n sigma square n, and the total signal power is L times P. So and BER OFDM from any standard textbook, if you assume relay feeding wireless channel, BER for OFDM is given by half 1 minus root SNR divided by 2 plus SNR. Now I can put the value of this SNR from this equation 1. So this becomes half 1 minus root LP n sigma n square divided by 2 plus LP n sigma n square. So this becomes the BER for OFDM. So this is we have done what we have done in this class is understood about starting with single carrier. Then we started with multi-carrier modulation system, and then with multi-carrier modulation system we went to OFDM, and then we understood the concept of cyclic prefix, how by using OFDM we are able to convert a frequency selective channel into n parallel subchannels which are flat channels, and then we had calculated BER for a OFDM signal, OFDM system. So next what we want to study is see the different subcarriers. It is possible that when the subcarriers are transmitted, there may be a shift. Suppose F1 was transmitted, and that F1 during the transmission there may be some shift F1 plus epsilon or F1 minus epsilon. So we want to study the effect of this epsilon. I mean, how does it change the orthogonality of the system, and how does it change the performance of the system? This is what we will do in the next class, and also we will discuss about the problem of PAPR, that is peak to average power ratio, which is quite common in OFDM. This PAPR is generally high for OFDM signals, and this is not a suitable thing or appropriate thing for our old optical wireless communication systems, because high PAPR will make the LED system go into a nonlinear mode, because it has only limited dynamic range, and then it is almost constant. So high PPR may pose some problem. So we are going to study about the frequency offset in OFDM and also PAPR. And then we will move to the next step, where we will see how OFDM can be utilized or can be made use of in optical wireless communication systems. Thank you.